Thank you very much. I'm really quite overwhelmed to receive this honor, and I'm very grateful to the university for giving me the honorary doctorate. What I'm going to try to do in my talk today in a fairly short period of time is explain some of the research that I did in the early years that were really the reason why I received the Turing Award. And I realize that many of you are not computer scientists, and I'm going to try and explain it in a way that I hope will at least make some sense to you. So Alan Turing, as Nuria pointed out, is considered to be the founder of the field of computer science, and he invented the stored program machine, which is really what we have today. However, he didn't have too much to do with the software that runs on these machines. And without the software, these machines would not do anything interesting. So everything that you use on your computer today is the combination of the hardware, which is what Turing invented, the hardware machine, and then the software that runs on that machine that causes it to do all the interesting things. And building these software systems is very difficult. The systems tend to be really big, millions of lines of code. What they do is very complicated, and to make it even worse, they might be distributed, running on many machines connected by the internet, they might be concurrent, and so on. And you would not want to program these machines using Alan Turing's machine, which would have been very difficult to use. Now, the question of how to address the complexity of software has been a major theme of research in computer science. And this research has taken two fundamentally different tracks. One of them has to do with figuring out clever ways to do things. So we understand now clever algorithms for searching and sorting. We understand how to communicate over the internet in a way that prevents the conversations from being listened to and so forth. And that is one area in which tremendous progress has been made. But that area, in some sense, is not the most important one for addressing complexity, because even when you understand how to build efficient algorithms to do certain things, this does not explain to you how to organize a huge software system into the components that allow it to do the entire job. And that problem has been the source of research in programming methodology and then later in programming languages, and that's what I'm going to talk about today. Okay, now I started working this around 1970 when I was working at the MITRE Corporation, as Nuria pointed out. As she mentioned, I did my PhD in artificial intelligence. I knew partway through that I wanted to move into software systems. And as soon as I left Stanford and started to work at MITRE, I started doing research in computer systems. Now, MITRE is a nonprofit organization that works primarily on contracts for the government to work on problems that the government has identified as important to them. And in 1970, the government put out, the United States government, Department of Defense, put out a request for proposals for research to try and address the software crisis. And what they meant by the software crisis was there were many, many systems being developed. People didn't know what they were doing. The software just didn't end up doing what it was supposed to do. And as a result, the entire project failed. And throughout the 70s and the 80s, there were many reports of disasters in which millions of dollars were spent, many man-years of effort were applied to the problem, and in the end you had to abandon the system because the software simply didn't do what it was supposed to do. So what the government was asking for in 1970 was ideas about how we could solve this problem. How could we develop software in a way that would ensure that it actually, at the end, did what it was supposed to do? And that is the field of program methodology. And program methodology actually addresses two separate but related questions. One is the design problem itself. Given the goal of building some system that's going to be a lot of work, how do you design it? How do you break it up into components so that it will, in the end, do what it's supposed to do? But the other part of it is, what are these components like? And I'm going to focus on the second part of this problem. I'm going to talk to you a bit about a couple of papers that were written at that time, because what happened when I got the Turing Award was I went back and I looked at the literature at the time that I made my discoveries. And it was extremely interesting to look at this, not only because these are excellent papers, but also because they give you a window into what it was like then and what has been accomplished since then. I'm just going to talk about a couple of them in today's talk. And the first one is a very famous paper by Edgar Dijkstra. He was from the Netherlands, and he wrote this paper called Go-To Statement Considered Harmful. It wasn't actually a paper, it was just a letter to the communications of the ACM, the principal publication magazine in computer science. And what's interesting about this paper is actually two things. One is it was extremely controversial at the time. And this is very amusing from the perspective of today, because if any of you who use programming languages know, the go-to statement, which is simply a statement that says jump your control to some other part of the program, doesn't exist in any of the programming languages we use today. At the time, though, people were concerned that it wouldn't be possible to have a programming language that could really allow you to write the software that you needed to write without the go-to statement. Additionally, they were quite insulted by Dijkstra's paper, in which he talked about how ill-structured the programs with go-tos in them were, and people complained that they wrote programs with go-tos and these were good programs. That's actually true. You can write good programs even if you have the go-to statement, if you focus on getting the structure right. The problem is, of course, that when you talk about teams of programmers and big systems where lots of people are working on them, you have to worry about the weakest link, the poorest programmer who is likely to misuse features like this. The other thing that's interesting about Dijkstra's statement is it's the beginning of the work that tried to put programming on a mathematical foundation. What Dijkstra said in this paper was, we need to be able to reason about the correctness of our programs. This is clearly very important if you want software to do what it's supposed to do. And he said, in order to do this reasoning, we have to work from the written program. We look at the text of the program, which is a static thing. We look at that statically. But we're reasoning about what happens when that text of the program is executed on a computer, which is a dynamic thing. And he said, the reason we don't want go-to statements is because we want the text of the program, the static part of the program, to be as close as possible to the dynamic part. And when you have go-tos, that isn't true. Okay, the second paper I want to talk about is this famous paper by David Parnas. Actually, Dave wrote two papers at about the same time on the structure of programs. And what David said in this paper is very telling, because he said, programs are composed of modules, but we don't know what these modules are. They're just things that are in these programs. Whatever they are, though, if we're going to be able to use them to decompose the program in a productive way, we have to understand how they are connected together. And then he has this famous statement in his paper, the connections between modules are the assumptions which the modules make about each other. So you have to understand this paper in the context of the time where people didn't understand modularity. Dave understood, many people working in the area understood that modularity was where we were aiming for, and he was trying to get at the issue of, if I'm going to have modules, how do I describe their behavior? Now I'm going to stop a bit and just talk about modularity because this was a very important concept. The idea that Dave was talking about is that you have a big program, but it's composed of modules. And so imagine I have a program with 1 million lines of code in it. What we're basically talking about is a divide and conquer kind of approach. We can't possibly reason about 1 million lines of code. It's just more than the human mind can keep track of. But maybe we can solve the problem by breaking the problem up into these modules, each of which is small enough that we can kind of comprehend what's going on. So the idea is each module is going to be a black box. What that means is on the outside we can see what it does, but we don't understand how it does it. And then on the outside we can use it just by knowing what it does. And on the inside, we concentrate on the question of how do we implement it to accomplish what it's supposed to do. And what's so powerful about this idea is it gives you two very important properties. One of them is local reasoning. We can reason about each module independently of the rest of the program. So we can work on 1,000 instruction chunks instead of millions of lines of code. The second is modifiability. If we don't like the way the implementation of a particular module works, we can simply re-implement it, And as far as the rest of the program is concerned, it's completely unaffected by this change. However, the situation in 1970 was, as I said, nobody really knew what modules were. The only kind of module they understood was the procedure. An example is a sort routine. You know that when it returns, the array will be in sorted order, but you have no idea how it accomplished that. So that's an example of a module. But procedures were nowhere near powerful enough to solve the problem of decomposing a big program into pieces. For example, a file system is not a procedure. And furthermore, they weren't used very much. I can remember, in fact, when I was at Harvard, I maintained a program with thousands of lines of code. And it was more or less just a straight line program. Every now and then it would call a procedure, and then it would just continue running. So it had no modules at all to speak of. Okay, so that was the situation in 1970, and I read these papers and a whole bunch of others, and I realized that when I was working on the Venus machine, which is something that Nuria had mentioned, where I had to build an operating system, I had actually invented a programming methodology, not because I was thinking about programming methodology, but just because I was worried about the problem of having to produce a big program with a team of programmers and coming out with something that I could understand that it worked in the end. And what I did in this methodology was I deviated from the standard way in which programs were built at that time. The way they were built at that time was there was a whole bunch of global state, and all the code manipulated this global state. And the problem was that there were many complicated connections through the global state. This is what Dave Parnas was talking about when he talked about connections. And in order to understand how they interacted, it got very complicated very fast. And so you really didn't have any reasonable notion of modularity because the connections were so complex. What I did in Venus was I said, we're not going to have any global state. Instead, we're going to partition the global state into these modules. Each module will own a portion of the global state. No other part of the program will be able to access that. And instead, if they need to access it, they'll access it by calling those operations. This turned out to be a very effective way to build Venus. As I said, I wasn't thinking about programming methodology at the time, but as I started to read these papers, I realized that there was one. So I wrote that up. Now, this is the 1972. I actually moved from MITRE to MIT in 1972. And when I moved to MIT, I was really focused on a particular problem that I really didn't have a way to solve, but I knew it was going to be very important. And the question was, there were these ideas about modularity. There were these papers describing modularity, like Parnas's paper. They always gave examples of how you might do a modular decomposition of a big program into chunks. But they had no rules. Modules were not well defined. And so when you tried to apply their ideas to some other system, it was completely unclear what to do. In a way, my paper was better than many because at least it had a rule about what a module looked like. But even then, it didn't really have much guidance about how would I invent one myself when I was designing my own program. So I was really focused on this question of how could we make progress? How could we develop this idea so that people who needed to design their own programs could figure out what the modules were going to be in a way that made sense. And sometime during the fall of 1972, I was fortunate enough to have one of these epiphanies, a magical moment in which I all of a sudden saw that I could take my idea of partitions and I could connect it to what I called abstract data types. And a data type is something that if you do any programming you're familiar with already, and programming languages at the time had data types. They had integers, they had floating point numbers, and most interestingly, they had arrays. And these were abstract in the sense that modules are abstract because they provided a certain kind of behavior. The programs used them just by calling their operations. And you never worried when you were writing the programs in the programming language about how they were actually implemented under the surface. So they already had a notion of abstraction related to this notion of modularity that I'm talking about. And in fact, the connection is very close. I'm thinking that the partition is an implementation of a data type. It has inside it a bunch of state, which is needed to implement the objects of the data type. But nobody gets to use that stuff directly. They only can call the operations. So it was a pretty direct connection between my idea about partitions and what I wanted to do. You know, what's interesting about research is that I look back now and I can see data types all over the literature about modularity. But at that time, people didn't make that connection. It's sort of after the fact that we can see that was what they were talking about. And I knew this was going to be a very important idea because programmers think in terms of programming languages. Data types are something they're already familiar with. And all I was doing was I was saying, it's not going to be enough to have a certain set of built-in data types. We're going to want to have methods that allow people to design their own. And those will be the big modules of your program. So that was fine. That was a great idea. But then the question is, well, how do you make it work? And the first thing that happened was in the next year, I started to work with Steve Zillis, who was a student at MIT, but an unusual one who was he was at his doctoral level and he had a lot of experience working for IBM, and he had some similar ideas, and so we spent that year trying to figure out what is this idea exactly. And my memory of the summer of 1973 in Cambridge, Massachusetts is that it was sunny every day, because Steve and I used to meet outside every day for lunch, and we would discuss our ideas, then we would separate and work separately and meet again the next day. Of course, this clearly isn't true, because it rains a lot in Cambridge, Massachusetts in the summer, but it's interesting how memory is not all that precise. At any rate, Steve and I had a very productive several months of this, and by the end of the summer, we had written a paper describing our ideas. This paper, Programming with Abstract Data Types, which was published in 1974. And what that did was it had sort of firmed up this notion of an abstract data type as being something where there was a set of operations and a set of objects, and as far as all the code on the outside could do, the only way to use the operations, but the objects was to use the operations. In addition, this paper had a sketch of what a programming language might be like. So what we had done in those 9 months or so is we had moved from this vague idea that a partition was related to a data type to the beginnings of a programming language support for that idea. And one of the things I meant to point out earlier is that programming methodology comes first and programming languages follow. So first you have to have the idea of how to do things. Then once you understand that, you can invent language features that would support that. Okay, so now we're at the fall of 1973, and what I did next was to follow up on this paper to develop a full-fledged programming language. And I did this with 3 students who showed up in my office in the fall of 1973, and they became the main designers and implementers of CLUE along with myself. This is the picture that Nuria had on the slide a minute ago. I would have liked to have showed you pictures of my students at that time, but I wasn't able to find them. Okay, so it was obvious that this was going to be the next step, was to go from that paper that Steve and I wrote. And Steve, by the way, was a participant in the design of CLUE, but he was doing his PhD thesis on specifications for abstract data types, so he wasn't one of the main contributors to the design per se. So it was the obvious next step, but there was a very good reason for following through from the ideas, which were still somewhat nebulous in that paper, to the full-fledged language. And those are the ideas I have on this slide. The first one is programming languages are the way that programmers understand what they're doing. And so by really defining a programming language that they could use, this was a way of really making sure that the programmers would understand what the ideas were. Another advantage of a programming language is if you write a big system in a programming language and then you see how it works, you know, the truth will out. If the idea wasn't going to work, we would see that the systems that we were trying to produce using the idea were not going to be effective. So it was a way of making sure that this was something that could be used in practice. Another thing is that a programming language is a mathematical object. It has a definition, and that way I could make sure that I had a really precise definition of what these mechanisms were rather than a sort of a hand-wavy, flaky definition. And finally, I could ask the question, even if I could make the systems work, maybe they didn't perform well enough. So I was able to look at that problem too. Now, I'm running short on time, so I'll go through this quickly, and this is probably mainly for people who are in computer science, just to show you a little bit of what was in CLUE. And I'm only going to show you a couple of the features. The first one was the cluster, which was our way of implementing abstract data types. And what's important on this slide is really 2 things. First is the top line, which lists the operations. So this is picking up this idea that I mentioned earlier, that on the outside, all you can do is call the operations. We're listing the operations there so you can see what they are. And then on the inside in red, I have some hidden information about the implementation. And include, this was truly hidden. There was absolutely no way that any code on the outside could get access to this information, and therefore I had that separation of concerns that I felt was so important to the notion of abstract data types. Okay, I'm going to skip that. The second thing I wanted to mention is the idea of polymorphism. So what I had on the previous slide was I had a set of integers. But we knew that we wanted something more general than that. We didn't want to have to build a set of integers and then later on a set of strings and later on a set of something else, because that would be very tedious to have to implement all this code that was fundamentally all the same. Instead, we wanted to build a definition of a generalized set where any type of element would work. And so that's what I'm showing you on this slide. And on the bottom of the slide, I'm showing you using the set where I'm saying, in this particular case, I'm using a set of integers. The reason polymorphism was difficult was because when you introduce parameterized modules like this, it turns out that not every type is a reasonable parameter. In the case of sets, you need an equality relation over the elements of type T. And an even more compelling example is if you had a sorted set, then the type T would have to have some sort of ordering relation on it so that you would be able to compare elements and see whether one was bigger than another. It took us quite a while to figure out the answer to this, but in the end we came up with this where clause, which we added to the header of the cluster to explain exactly what operations the parameter type had to have. And once we had that in place, we could guarantee in the compiler that whenever the type was instantiated, which is what I was doing at the bottom of the previous slide, whenever I say this is the type I want to use this time, that it actually had the operations that were required in the implementation. Okay, procedures had some other mechanisms that I won't talk about, and I just want to finish up with a couple of slides about what happened after this. I moved into distributed systems. And the reason was that I was looking around for a project to do, and this is probably 1978, 1979. It took several years to design CLUE. And I saw the ARPANET, which is the precedent, the preceder of the internet that we know today. And there was a dream in the ARPANET that we could write distributed programs, which of course we have huge numbers of them today. These are programs that run with components on many machines connected by a network. Nobody knew how to do this, so I thought, here's a marvelous research area, and so I decided to work next in distributed systems, although I continued to work for all the time on programming methodology. So, you know, where are we now in computer science? So when I got the Turing Award in 2009, my husband was online every day looking at what was being said on the internet. And as you know, the internet is an interesting place. People are saying nice things, they're saying not so nice things. You have to take it all with a grain of salt. But it was really interesting because there was so much chatter going on. And one day, he came across a quotation which said, "Why did she get that award? Everybody knows this anyway." Now, this was obviously not intended in a nice way, because they were trying to say, I didn't do anything, everybody knows it, and so forth. But in a way, it was a huge compliment, because the truth was, everybody does do it this way. But when I began, and the work that I did, they didn't do it that way. So this was really, in some sense, an amazing discovery for me, because I hadn't been paying any attention. I'd been doing my work in distributed computing and replication algorithms and so forth, and I hadn't thought about programming until I got the award and I started to think about it again. I also discovered my students thought everybody does it this way. So it was really very revealing. Okay, that doesn't mean that we're done, though. And I'm just going to mention a couple of research challenges in the area of programming languages and methodology. This is one that's kind of dear to my heart. I don't know if it's doable. What you see if you look at computer science in universities is that the languages that people are teaching the introductory courses in are not the same languages typically as the ones that are being used in industry to build the big systems. And the reason is that the industrial languages are very powerful and very complicated, and they get in the way of teaching the introductory courses. And this matters because the introductory languages don't have good abstraction mechanisms. They don't have support for modularity the way that I described it. And unfortunately, people often stop learning about computer science after those introductory courses, and they start to build big systems in these languages, and then they get into trouble because they don't have good modularity support. So why couldn't we have a language that we could start in the first course in computing, and then it would have the right features so they could go right on and use it to build big systems? The second problem I wanted to mention is about massively parallel computers, which are all the rage these days. And people are talking now about computers with hundreds of cores, and they're talking about in the future computers with thousands of cores. Now, just because Intel wants to sell us these machines doesn't mean that they are necessarily going to be the right thing, because unless we can figure out how to use them effectively in the software, all that extra parallelism is not going to be good for anything. So this is a major research problem in computer science today. Can we figure out how to make software run in an effective way on massively parallel computers? And I actually think this is a problem in program methodology. We don't know how to write those programs yet. And if we can figure out effective techniques, then we can move some support into programming languages. And that's the end. Thank you.